Hello? Hello? Okay. Let's start. Good afternoon. I hope you are all doing well. It's a pleasure for me to give a talk at CoreOS Fest. My name is Victor Hu, Victor Hugo without Go. I'm a developer from Huawei, and but recently I have been acting more like an operator than a developer. For I have met a lot of problems when integrating Kubernetes into our internal platform. But fortunately, Kubernetes provided a flexible and extensible way which helped us to solve the problems. I'm glad with that. So I can consider myself practicing DevOps. And today I'm going to share this flexibility Kubernetes provides in today's talk. Here's my contact information, my email address, and GitHub account. Usually people will put their Twitter account here. I do have one, but for well-known reason, I have trouble to access it, so I didn't put it here. Let's go back to the title. Today I'm going to talk about the pluggable Kubernetes. And as you can see, the subtitle is Deploying Telecom Applications with Kubernetes. So what are telecom applications? I work for Huawei, and Huawei makes cell phones. Maybe some of you are using a cell phone from Huawei. Myself is also using a Huawei cell phone. But besides that, Huawei is the world's largest telecom vendor, and it provides network infrastructure and related software to telecom operators. When you make calls, surf the internet, there will be a lot of applications running in the background, which ensures your voices, your requests, and responses are delivered to the right place. And of course, some of them will calculate how much the voice or internet service will cost you. These services dedicated to provide communication service, we call them telecom applications. There are some characteristics of telecom applications. First is large scale. For example, one of our customers has 500,000 service instances running in one of its data center. And 2 months ago, we updated that data center. That was really hard work. The second is there are lots of monolithic applications. For historical reasons, some old applications may not have a well-decoupled architecture. And when more and more features were added to the application, it grows larger and more complex. So since it's larger, it takes more time to deploy it. And it also reduces the flexibility. That means any small change requires building and deploying the whole application again. And monolithic applications leave a lot of unsolved technical debts. There are two reasons lead to this situation. One is to fasten time to market, people usually choose a faster but not a better way to implement the features. And the second is an altitude used in a wrong place. That is not broken, won't fix. And as the application grows into a giant, refactoring it becomes mission impossible. 2 weeks ago, Kelsey Hightower posted a tweet saying, when people say moving to microservices, I hear declaring technical debt bankruptcy. So today, some telecom applications also move to microservices, and they're going to work together with old monolithic applications at the same platform. Telecom applications requires high performance and availability. About performance, telecom operators serve billions of people in the world. The daily traffic is already a huge number. So, and when some event happens, such as Black Friday online sales or Chinese Spring Festival, there will be an explosive growth of the traffic. Can you imagine hundreds of thousands of people making calls at the same time in one square? The network load is 140 times than usual, and wireless signals will interfere with each other. Even at some conferences where there will be people complaining the slow Wi-Fi connection. About availability, when you access a web service, if the backend the service is down but restored before you take the next step, it does no harm. Unlike web services, voice services are continuous. If you are making a call, the break of the call will bring a bad experience. And if you are in an important business call or talking to a girlfriend, it's more than bad, but sad. There is a common understanding for telecom devices. It requires a reliability of finite, that is 99.999%, and we're pushing it to 6 nines. Usually, we don't need to modify the kernel to run our applications, but for telecom applications, it happens very often. The consequence is that we cannot treat all the underlying computer resources as the same, even they are in the same resource pool. For applications, requires a specific kernel cannot share resources with other applications. And the last, customer requirement varies. Actually, it happens to every company. One little difference is services facing individual person, they may focus on meet the majority's needs. But for us, we must satisfy every of our customer. These characteristics are not unique to telecom applications, actually. And the problems they introduced is also common. For large scale, the problem is how to handle high traffic. And for monolithic applications and microservice, it's mixed deployment. And for the rest, resource isolation. Actually, there are more. There are some principles when we use Kubernetes. I must emphasize, this is our principle, not for all person. Firstly is we need to meet different customer needs. Actually, we are providing products and helping our customers to build their services. So we must customize the product for each customer, which requires the features must be scalable. If one customer likes the feature, we add it, and if others don't like it, we simply remove it. The second is we don't want to detach with the community. There will always be new exciting features coming out when Kubernetes publishes a new release. Though we're contributing to Kubernetes, we still want to keep synchronized with the latest version. These two principles lead to a same result. That is, we must leverage Kubernetes plugin mechanisms as much as possible, or develop features with code decoupled with Kubernetes, so we can add or remove them freely, or upgrade to the latest release without manually refactoring or rebasing the code again and again. I believe nobody likes rebasing. Kubernetes already provided some plugin mechanism. We have network plugin, authentication and authorization plugin, and volume plugins. Actually, volume plugins are slightly different with the others. We should say volume drivers. It allows Kubernetes to use different volume management tools. Here I need to say Huawei has just created a new volume management tool, especially for container. It's called Elara, and we are going to open source it very soon. One of our problems is some applications cannot be containerized. one example is a database we're using. I should not mention its name, and actually it doesn't mean it cannot run in containers. Just the vendor suggests not to, and they will not provide technical support if we use it in containers. Maybe people would ask, why don't you move to other databases like MySQL? I have to say the database we are using has its own advantages like higher performance and reliability, but it's another topic. So the situation is the database is outside the management of Kubernetes. Our problem is to let Kubernetes be aware of the database and allow the applications it manages to access the database. We use Kubernetes services and endpoints resources. Kubernetes service is a good abstraction of multiple service application instances. It looks like this. A virtual service object is exposed to user and some pods are backing it. When we create a Kubernetes service, we give it a label selector, and Kubernetes will use this label selector to find out the pods with same labels and create endpoint objects for it, which indicates the relationship between services and pods. So in this situation, we can manually create a service, but give it no label selector. This service has a name, my database, and after that, we can create the endpoint manually. Because the service itself don't have a label selector, Kubernetes will not create endpoint object for it. After we've done that, when applications inside Kubernetes access this service, the traffic will be routed to the addresses listed in the endpoint object. The good thing is manually create endpoints allows users to plug external services into Kubernetes cluster as a service. Other applications can use it as native service. But compared to Kubernetes managed services, we need to handle the failure by ourselves. For if the background service fails, Kubernetes cannot recreate it. Talking about Kubernetes service again, there are two main functionalities of Kubernetes service. One to find out and maintain its backend pods. Another is to route traffic to the right backend. The problem on service proxying is it depends on IP tables. When we use user space mode, kubeproxy will install the one rule in IP tables. And if we are using IP tables mode, kubeproxy will install the rule for each backend point. So as the service number grows, there will be too much IP table rules there. It reduces the traffic routing performance. We know telecom applications requires high performance. For these applications, we cannot rely on software routing. We must do load balancing outside Kubernetes by ourselves. To do load balancing, so the first thing we need to do is to find out the service and its backend points, backend pod. There are two ways to register a service instance: self-registration and third-party registration. Self-registration is simple and easy to use, but it requires the application itself to implement the registration code. When applications are using multiple programming languages, then you will get a headache. Let's consider third-party registration. Actually, I think Kubernetes is a good service, third-party. It has already done the service discovery work. So the problem turns into, we want Kubernetes to do service discovery for us, but we don't want it to do any traffic routing. In this case, we can use headless services. The difference between a headless service and a normal service is that a headless service don't have a cluster IP, and kubeproxy will not do any traffic routing for a headless service. But still, headless service will create endpoint objects to maintain its backend ports. So with Kubernetes, if you use DNS to look up a headless service, all the addresses of its backend ports will be returned. So with headless services, we can do load balancing outside Kubernetes using whatever device or software we want to use. But people will ask, if my applications are already self-registering, why would I need this headless service? That's right. Actually, you don't need it. But I think Kubernetes provides free choices for users to choose what technology they want to use. Personally, I'm pleased with that. Sometimes performance of API server may be the bottleneck of the whole system. As mentioned before, telecom applications are complex, and they may have a lot of coupled components. So when updating a system, we cannot do as flexible as microservices, which can update a component, one single component. We must if we want to update a telecom application, we need to update them all together. And when this happens, there will be a lot of traffic coming out from one user or namespace. We must consider, in this situation, this situation may reach the maximum capacity of API server and chokes it from serving other users. We must consider other users' experience. To ensure the requests from other users be handled, we need rate control for API server. Actually, internal instances of, internal components of Kubernetes, like scheduler, kubelet, and etc., they all have rate controls, which ensures this component wouldn't send too much requests to the API server at a time. But what we need is the API server to deny some of the requests from a certain user, but let requests from other users coming in. It's like a quota. Every user has their quota of sending how much requests to the API user at a period of time, and when it runs out, the requests will be rejected. Adding this feature to API server does seem to be hard work, but due to the principle I have mentioned before, we don't want to invade the API server's code, so we need to find another way. We know Kubernetes have resource quota management. How is it managed? We looked into the API server and found the validation of resource quota is done by admission controllers. An admission controller is a piece of code which intercepts requests before an object is stored. There are multiple admission controllers in API server. Some admission controllers just verify whether the request is legal. Some admission controllers will add default values to an object. But the most important thing is admission controllers are pluggable. We can easily add or remove one admission controller by editing one flag of API server, which inspired us. So we created a new admission controller. It uses token bucket algorithm to control the rate. it solves the problem to some extent. Why I say to some extent, actually, it's not a perfect solution. As we can see, API server admission controllers is in the middle of a request handling process. So it cannot reject the request at the first place. And since it's like a quota, I think a better way is to put the limit into resource quota of a namespace. But we are managing it in the admission controller we have developed. So I think there is a large space to improve the solution. Here is the common scenario on resource isolation. Platforms will serve multiple tenants, whom we also call users. Assuming we have a VIP user, and there are some resources are reserved for him to use only. At the same time, he can also use the resources in public pool. For other users, they can use only resources in public pool. Actually, we can use labels or node affinity to deploy the pod to or not to certain nodes. But we cannot force all our users to label or annotate their pods. So how to avoid deploying the pod with no label to the resources reserved for the VIP user is our problem. We looked into the scheduler. Basically, the scheduling process has two steps. First, use predicates functions to filter out the nodes do not meet the pod's requirements, such as CPU, memory, disks, and the labels. And the second step is to apply priority functions, which gives a score to every remaining node. And the node with highest score will be the deploying target. These predicates and priorities compose a scheduling algorithm. So to solve this problem, we just need to add a new predicate function. For normal users, it filters out the resources reserved by VIP users and add a priority function. For VIP users, it gives higher score to nodes in their private pools. Adding priorities and predicates is the easiest way to extend a scheduler, but it also has its drawback. First, it invades default scheduler's code. And second, every time when you modify the predicates and priorities, you need to recompile the scheduler's binary, replace the old one, and restart it. So is there any other way to extend the scheduler? Looking at this picture, we can find, besides predicates and priorities, there is another component of a scheduling algorithm. That is extender. We can use extender to allow third-party processes to filter and prioritize the nodes. We can do whatever in the external process. And we can use policy config file to configure a scheduler. It describes the predicates, the priorities, and the extenders we want to use to start a scheduler. As the extender kicks in, the scheduling process turns into 4 steps, but we don't need to go through all the steps for the extender. It depends on the configuration. And last, extender provides a better extensibility. we don't need to modify the scheduler itself. But its weakness is also obvious. It uses HTTP calls, which is slower than in-memory calls. So for platforms which requires high scheduling performance, maybe it's not suitable. Another approach to extend the scheduler is to use multiple schedulers. Since schedulers are well decoupled with other components of Kubernetes, why don't we start a new scheduler? And we can customize our schedulers and run it alongside with the default scheduler. It brings in a new problem, that is, one pod cannot be scheduled by two schedulers. We must make a decision who is in charge of scheduling the pod. We use this annotation to assign a pod to a scheduler. And there are two places to make this decision. The first is before a pod is saved. We can use admission controllers to add this annotation. It works, but has a disadvantage. If the scheduler running in the backend is down, how to clean all the unscheduled pods which has already assigned to this scheduler will be a trouble. Another place is before the pod is scheduled, we can create a controller, not an admission controller this time, but like node controller, auto-scheduling controllers. This controller watches status of schedulers and dispatches pods to schedulers. If a schedule is down, it can find out and reassign the pods to other schedulers. So with multi-schedulers, we don't need to restart it. And there are more workers scheduling pods, so it is fast. But it also brings in extra complexity. For there are more schedulers in the system, the higher the chance will be the higher the chance conflicts may happen. Now I have introduced 3 ways to extend a scheduler. They all have their advantages and drawbacks, but they are not exclusive. We can choose one or more approaches to solve our problem, depending on our scenario. Finally, a brief summary. There are a lot of places can be considered as pluggable in Kubernetes. I put them into 3 categories. First is built-in. There are network plugins, auth plugins, and volume plugins. Second is configurable, but we need to restart some of the Kubernetes components. There are admission controllers and scheduler algorithms. And the last is replaceable at any time. Scheduler instances and scheduler extenders are of this type. I also put endpoints and headless services here, though they are not really plug-in, but they do provide good extensibility. And Kubernetes, its simple design philosophy has hide many complexity, but itself is complicated. So I think there are more features for us to discover. Okay, thank you. So do you have any question? Yes? Can you speak slowly? For I'm not a native speaker, I may have troubles understanding you.
Absolutely. Okay, so my question is, since you're running these telco applications on Kubernetes, how do you guarantee that the Kubernetes node is not kind of restarted in the middle of a phone call? Do you have some kind of draining mechanism?
No, we cannot guarantee the node won't get started. We only guarantee the application won't get started. Actually, we are treating the applications like pets, not cattle. Oh, by the way, if the node fails, we still use, actually, we cannot control the node itself. We still use its backup nodes.
Yes, so I wanted to know, how do you manage the multi-tenancy? Do you have some kind of isolation? You have the scheduler, I understood, but how do you manage network isolation? If you do.
Actually, we are not using Kubernetes in such large scale. So we do not have a lot of tenants. If we don't have much tenants, and to improve the performance, we are using hosted network. So we use routers, switches to isolate the network physically.
Thank you.
Anyone else?
If no more questions, thank you. Thank you all.